turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. I'm Chris Smith, and this is the show where we bring you the latest breakthroughs and hear from some of the biggest names in science, technology and medicine. Speaking of which, this week we're hearing from the man who put the Milky Way and dark matter on the map, and that is Gerry Gilmore.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
In the first half of the last century, scientists realised that there must be more to space than meets the eye. Without some invisible force hanging onto them, clusters of stars rotating around galaxies ought to be being flung off out into space, like children letting go of a playground roundabout. That force, they knew, must be gravity, but its origin, where it was coming from, no one knew. A popular theory at the time was that millions of stars we couldn't see were lending their mass to the equation, but by carefully logging what was out there in our own Milky Way galaxy, Gerry Gilmore showed that the postulated legions of small stars didn't exist, and therefore a much more exciting but totally intractable entity was probably at play. Dubbed cold dark matter, we can't see it or measure it, but it accounts for 5 times as much mass as the matter that we're made of, and it's probably largely responsible for the way the universe and its subsequent flotilla of galaxies have evolved after the Big Bang. Gerry is Emeritus Professor of Experimental Philosophy at the University of Cambridge's Institute of Astronomy. Supervising himself for a PhD in physics in his native New Zealand, his studies subsequently redrew the map of the Milky Way, showing us that there's far more out there than we first thought. Latterly, he's led the Gaia space probe mission that put a gigapixel camera into deep space orbit to catalogue billions of stars and look back in time across the evolution of our galaxy. It's the 10th anniversary of the launch of that mission this week. We met at Queen's College in Cambridge to hear his story, beginning with what we knew about the universe back when he began his studies at the University of Canterbury in the early 70s.
in a funny way, it was an exciting time, but it was also a very primitive time. People were just starting to realise that there was information available in the types of stars and their chemistry and the way they were orbiting around in the Milky Way that was telling us something about how our galaxy, our Milky Way, might have formed. But this was pre-digital, so the picture we had of the Milky Way was not much different than it had been in the 17th or 18th century, actually.
Did we have the concept of what a galaxy actually is by then? As in, galaxies are groups of stars, am I right? And they're in their neck of the cosmic neighbourhood, and there are billions of them.
Yeah, actually, this is the centenary of that discovery, strangely enough. People don't realise it was actually in 1924 that the first galaxy exterior to the Milky Way was shown to be in place. It's a little dwarf galaxy. It's near us. It has the exciting name of NGC 6822, a rather under-interesting, middle-sized galaxy that's halfway between us and the Andromeda Nebula. But in 1924 was the first time that anybody, that was Hubble, using the Henrietta Leavitt Cepheid distances, had shown that something was actually outside the Milky Way. They hadn't even proved that for Andromeda at that stage. That took a year later. So it was just 100 years ago that people had discovered that the universe is a big place.
They originally called those structures we now know are galaxies nebulae. Did they just think then that the universe was essentially one massive galaxy and there were some bits of it that were farther away than others, and that's why these stars appeared as distant smudges or nebulae? They didn't have that concept of they're aggregated together in their neck of the cosmic woods, as it were.
Yeah, that's certainly true. Remember the Einstein's equations and their solution came about largely in 1919 after Eddington's eclipse. So for the first 5 years of cosmology, where people were talking about expanding universes and contracting universes, they were actually talking about the stars in our Milky Way. That was the whole of the universe for them in those days.
So when you began your academic career in the 70s, what were the big questions that you thought, that's what I want to get my teeth into?
Well, I did my PhD I didn't have a supervisor. I just read the literature and found out what was interesting. I was all on my own in New Zealand and discovered that there were these exciting things going on related to giant black holes in the centres of galaxies and their observational evidence, which is something that was called a quasar, a quasi-star, because they looked superficially like a star, but they were clearly not stars. And it was in the late 60s that Donald Lyndon Bell, who was later here, and Martin Rees, who was later here, first proposed that all galaxies have these things in their centres. But it was quite hard to prove that that's what they were. All you knew was there was something that was producing a lot of energy. So the key, and this is what I decided to work on, was to say, well, if they're small, they must be able in principle to change their brightness quickly. And if they're big, they can't. So if you've got something that's, say, 1,000 years across, the fastest it can change is on a timescale of 1,000 years. It takes that long for the light to get from one side to the other. Whereas if you've got something tiny, it can change overnight. So I went looking for fast changes in quasars to try and show that there was something complicated and black holey in the middle of them. And that was eventually proven par excellence. Only a few years ago, with the Nobel Prize given for people discovering the black hole in the centre of our own Milky Way, showing it must be a black hole. But that, at the time, struck me as a fun thing to try and work on. Turned out to be too hard.
What did that unlock the door to, though?
As I said, I was all on my own in New Zealand, being a sort of ignorant, unaware of how the system worked. But fortunately, there were kind people who took pity on me and arranged that I should then be offered a job in Edinburgh. This was incredibly lucky timing because it was the dawning of the digital age. So in that period, digital meant scanning a photographic plate because there weren't digital detectors. But they'd just built this new machine in Edinburgh to try and scan photographic plates and get the information into a form that one could do something with.
Do you mean as in objectively? So rather than just look at something and subjectively say, well, that looks brighter than that, you can actually read how many silver grains there are on the plate and say, well, that must be brighter than that.
That's certainly what this machine did. It was called the Galaxy machine. People used these silly names at the time. So these scanning machines were the first that would actually take a great big photographic plate and give you quantitative information on millions of objects from those plates.
Presumably these are stars and presumably our galaxy, the Milky Way.
You obviously know more about astronomy than I did at the time because we didn't know that at the time, actually. So with this brand new measuring machine, I thought, well, I'll go and find a whole lot more quasars, okay? So this got to be easy. All I have to do is measure all of the point-like, star-like things on this photographic plate, calculate how many should be stars just by building a model of the Milky Way, subtract that off, and whatever's left's got to be quasars. Incredibly naive. So I started to do that, and then I realised that actually there wasn't a model of the Milky Way that corresponded even remotely to the number of stars I was seeing on the sky. And so put briefly to one side the quasars and haven't quite got back to them yet.
Was this really someone asking for the first time, well, how big is our galaxy? How big is the Milky Way? How many stars really are there in it? Did we have no insight at that time to the answer to that question then?
No, there had been some awareness, particularly of the disk of the Milky Way, where radio astronomers and people back in the 30s and 40s had discovered that the Milky Way was a rotating disk. So that was known. But the thing I was doing was looking up out of the disk of the Milky Way. See, I mean, anybody who's ever been out on a dark night, particularly in the southern hemisphere, knows what the Milky Way looks like. I mean, it's a thin band on the sky. So what I was doing was looking up away from the bulk of the stars and away from all the gas and dust and such like, and looking therefore, as I thought, out of the Milky Way into a place where you would only find things beyond the Milky Way. But it turned out the Milky Way has a lot more stuff up there than we'd thought, and so I discovered that completely rebuilding of the structure of our knowledge of the Milky Way.
Was that just our naivety that we thought it's a nice thin strip and when we look out of it we're looking out into outer space, and in fact it's just a bit wider and broader and we're embedded in the middle of it? Is that why we would see that, or is it more subtle than that?
No, it is pretty well that. I think it just hadn't occurred to anybody to ask the simple question, does it look more than the obvious?
We say that there's probably a couple of 100 billion stars in the Milky Way. Was that your number? Is that how we arrived at that number?
Actually, that number comes from a different thing that I did, which was a follow-on from this original stuff. Because at the time, the rotation of galaxies was being measured with radio telescopes mostly. People were starting to understand about dark matter. It wasn't really widely accepted, but it was understood there must be something going on. But the most conservative explanation of what dark matter was just more of the same. So lots of low-mass stars and planets. And so a very large number of people, including Mort Roberts, the first guy who realised that there was dark matter in galaxies. I remember he was over on sabbatical here, and he spent months trying to persuade me that all the dark matter in the universe was made up of faint stars. So I started a program with a PhD student to just go and determine exactly how many low-mass stars there were, which turned out again to be quite easy with the technology of the time and some, to be honest, rather clever computer modelling. We developed the first ever, with hindsight, reliable description of the relative number of stars as a function of their mass, and showed unambiguously that the number of low-mass stars, which had they been common, would have dominated the mass of the galaxy and of the universe, was actually very small. So the average star is about half the mass of the Sun, and as you go down in mass, although you go down in light rapidly, so you can't see these things, the numbers go down too.
Just to clarify what you're saying, people had thought that this phenomenon we now call dark matter, that was a phenomenon that there were just lots of very small stars that were lending their gravity, and that would account for the behaviour we see of how things work in a galaxy. But in fact, when you went looking for how many of these small stars, there just aren't enough of them to account for it on that basis, so it has to be something else.
That's pretty much it, yeah. The awareness that there was something important called dark matter, the awareness that there was a lot of this stuff everywhere and how important it was just growing through that same period, through the 70s. Most of the evidence came from two separate things. The first was just a theoretical expectation that the first stars and galaxies in the universe would never have formed unless there was a lot more matter around to gravity to pull them together than we seem to be able to account for. And that was the main explanation. The second explanation was a bit indirect, and it was the fact that we see lots of galaxies like our Milky Way, which are rather thin when you see them edge on. And these galaxies seem to be quite common. They're very thin, and so they're obviously able to live like that for a long period of time. Whereas some elementary mathematics would tell you that that's not possible. They're not stable. They should just crumple up. But these things clearly do exist, so some smart theorists said, well, there must be, therefore, a lot of mass in a big round halo around these stars, much, much more than corresponds to the light. And so that was the evidence, the first evidence from mid-70s, that there was dark matter associated with galaxies. Before that, we didn't know, because we didn't know how much a galaxy weighed, so it didn't matter how fast it was spinning, you had no idea. What it could have been just stars. So those two things were coming together at the same time. And then by ruling out the fact that it was just very faint stars, it became apparent and very rapidly accepted over the next few years that this dark matter must be something quite different than ordinary matter.
Presumably from your observations and then calculations, that meant you could actually weigh a galaxy. You could work out how much mass there must be in your average Milky Way.
That's correct, yes, and that's another thing I did at exactly the same time. It's a bunch of really smart PhD students, fortunately all cleverer than me. And so with another one, we actually, for the first time, determined how much dark mass there was near the Sun and how it was distributed vertically. We had the good data. This was the same data as I needed for discovering the structure of the Milky Way. And went out and got the speeds of loads of stars so we could measure how fast stuff was moving. And from that, were able to do the first robust measurement of how much dark matter there is near us, near the Sun. And that number's still accurate, actually. Turns out the equivalent of about a third of a proton per cubic centimetre, which doesn't sound very much, but there's a lot of cubic centimetres in the universe.
Does that then align with... We accept that maybe 20-something% is dark matter, but do we have the same amount of dark matter around us as if I looked much farther afield in the universe, or does it aggregate much more strongly around where we are?
The distribution of that stuff is very, very lumpy in the universe. So the idea is that this dark matter and all the matter would have been spread out pretty uniformly straight after the Big Bang. But the Big Bang was a bang. There are sound waves, acoustic waves as we call them, but sound waves bouncing around all over the place. And wherever you had the peak of a sound wave, there were sound waves through the matter, there was a little bit more matter there, and so the peak of a sound wave was slightly heavier than the trough of a sound wave. And over time, these peaks built up and built up, and they sucked the matter out of the troughs, and so the contrast became greater and greater. And so this led to a huge web, it's called, a system of filaments running out through space. And whenever you had a slightly denser part in a web, you would form a galaxy, like our Milky Way. And so the growing awareness was that that's the way structure in the universe grew, and therefore, on average, round a galaxy, you'd find 8 times more dark matter than you would find ordinary matter.
Did dark matter drive that early evolution of the universe then? So in other words, it was the force that then pulled via gravity the matter into the configuration it's got? Or were they both mixed up together and they just followed the rules of gravity?
You're exactly right. The key thing about dark matter and why it's called cold dark matter and why it was invented in the first place, and now we know it's the answer to the problem, is that if you just had ordinary matter, the universe was so hot that the ordinary matter was all ionized, and the heat and the radiation would have dragged the matter with it. And so it would have just kept spreading out and spreading out and spreading out, and there wouldn't have been anything lumpy like a star or a galaxy forming at all for quite a long time. And so it was realized that there must be some sort of matter that doesn't get dragged along by light. And so that's how it was realised, not only that you need dark matter, but also that this dark matter must be of the type whose technical name is cold, so that the light couldn't drag it along. And so that means this dark stuff, because it wasn't being dragged along, could start peaking up in these sound waves, while the ordinary matter was still being spread out smoothly. And then these peaks and heavy bits were there, so as soon as the light and heat thinned itself out enough that the ordinary matter got let go, it could immediately fall into these piles of dark matter that are all already sitting there and just sort of beckoning with their little gravity fingers, say, come join me.
Once you had that sort of insight, what was the next big question to ask?
Well, the next thing that I moved into was, until the early 1930s, it was believed that the pattern of chemical elements like we have on Earth was universal, and so all stars and everything else was made of the same as on the Earth. That's a reasonable assumption to make.
Would that be because people thought perhaps the Big Bang created all the elements at the same time then, so space was born with all the elements, or did they have some kind of view as to why all those elements could be there? Because the Big Bang only gave us hydrogen, helium and a whiff of lithium. To invoke the existence of all of the elements we have here, they'd have to have some kind of mechanism for where they all came from.
That's true, but none of that was known until the 1950s. You've got to remember, nuclear physics was invented in 1939, right at the start of the war, which is why there was the Oppenheimer and all the rest of it. So through the 30s and 40s, early 40s, people just didn't know where the elements came from, and so they just assumed that what we see now must be what you've got, and it's got to be the same everywhere. They knew that Jupiter and Saturn were different because they're full of methane, but they didn't know why. But then there was this genius here at Cambridge, Cecilia Payne, motivated by Eddington and worked with him a bit, and then was able to go to Harvard. And her PhD thesis was the first evidence that the universe was mostly made of hydrogen. So she applied that to spectra of stars and said, hey, they're all made of hydrogen, they're not made of rocks. And it took a small number of years till this catch on, and this just revolutionised all of astronomy. And then through the 1950s, when all the nuclear astrophysics stuff was declassified, then the whole new subject was created. And this was famously done by two groups, one a guy named Cameron in the US, but the other by a group associated with Cambridge in the UK, which was Fred Hoyle, Willie Fowler, who was an experimental physicist from Caltech, and two Burbages, Margaret Burbage and Jeff Burbage. And they just calculated the origin of essentially every type of star. Therefore, the number of chemical elements in a star must tell you when the star was formed, because it just takes generations of stars to build up all the chemical elements. So if you found a star that didn't have many chemical elements in it, it must have formed before one that had lots. And so that gave you a sort of clock. That was the realization that if you had a clock, then you had some way of understanding or probing the evolution of a galaxy. So that was the beginnings of this concept that galaxies retained in their properties some story of their own history. And so you could do some sort of archaeology.
And that's, of course, become the story of your life in recent years. I think you first had the idea for what became your Gaia mission in the late 90s, and that's all about archaeology, really, but on a galactic scale. Is that right?
That's exactly right, yeah. I mean, as soon as you got to that stage where you need to know something about the properties of how a star is moving, i.e. its orbit in the galaxy, which links into how the dark matter is distributed because it's orbiting through the dark matter and so they're connected, and the chemical properties of the star so that you can know roughly how old it is and what generations preceded and post-dated any particular thing you measure. Then the big challenge was to say, well, let's get some evidence for that. Let's measure stuff. And for that, you need to measure a lot of stuff. And the new technology of space science was just, again, moving up to that scale of capacity. And so it became possible to pose that question and actually try and answer it through experiment, which is what Gaia has done.
We should tell people a bit about Gaia and what it is. I mean, this was big budget stuff. But so obviously people believed in you when you and your collaborators proposed the idea to do this. This is not just a simple telescope, kind of let's do a bit of astronomy. This is Large Hadron Collider type level of investment, wasn't it, that went into this?
Yeah, it was. I mean, and it didn't just spring out of the blue. There had been a small precursor which tested the concept. From space, if you lock two telescopes together in exactly the right way and scan the whole sky, then you can very accurately measure where stars are out to a fairly large fraction of the whole of the Milky Way. Totally revolutionary. And you could scan the whole sky, so you could do it for 1 billion stars rather than a few thousand. Also, we'd realised that our previous understanding of the structure and shape and properties of the Milky Way was completely wrong. And so there was an awful lot to learn. And so all of those questions just fell together into what the European Space Agency calls a large mission. And these are large because their budget is large and they take a long time to build and an even longer time to operate. So Gaia just this week reached its 10th anniversary of scientific operation. And in that time has measured 250 billion measurements.
What is it revealing to you, and why is it important? What is this teaching us?
What Gaia does is do the same as your eyes do. Your eyes judge distance from that slight angle between your left eye and your right eye. Your brain does it without you being conscious of it. We do the same thing with Gaia by looking from one side of the Earth's orbit and the other side of the Earth's orbit. So our head is twice the size of the solar system, but apart from that, it's the same principle. And so we can measure the distances to stars pretty well out to the outer parts of our own Milky Way. And in fact, in special cases, we can see stars in the Andromeda galaxy moving. The idea is that by repeated measurements and building up measurements, you can discover not only how the average thing is moving and what the average bit of Milky Way is doing, but you can also look for patterns and groups of stars with special properties. And these are the interesting things because particularly when you're up far out of the disk of the Milky Way, things change very slowly. I mean, space is big and it takes a long time for things to go around the Milky Way. So things in the outer parts have only been around a handful of times over the whole history of the universe. And they're still moving as they were when they first came into the Milky Way. So we can unpick the history of the Milky Way by looking at these streams of stars and clumps of stars and patterns of stars. And at the same time, we can measure what chemical elements they're made of and therefore their age. And so we can literally untangle the evolution and formation and assembly history of the Milky Way. And that was the goal, and it's been achieved par excellence. As well as operating for 10 years, the Gaia mission has now just published its 10,000th technical science paper, which is about 5 times more than Hubble telescope's done. I mean, it's just blown the record books apart for its impact on astronomy. It's just revolutionised everything, literally.
If you can make those sorts of inferences about the behaviours of these stars right back to the origins of our galaxy, has the Milky Way always existed as just its own entity, or has it almost hoovered up other galaxies or run into other galaxies which are on a collision course? And if so, what happens when that sort of thing happens?
Yes, that is what happens. And in fact, that was the other sort of missing bit of motivation for Gaia. We discovered the Sagittarius dwarf galaxy, which is a dwarf galaxy that's actually merging into the Milky Way as we speak. It's across the other side of the galactic centre, so it's not. Otherwise, it would be a big bright thing on the sky. You'd see it easily. But this was, to use that revolting term, which was widely used in the US press, this was the smoking gun that galaxies gobble up other galaxies and grow by accreting. And that was speculation in the early 90s until we saw it actually happening, and you can see this stream of this thing going right across the sky as it's wrenched apart. So that process of galaxies growing by other galaxies still continues today. But it's also a mistake to think that there was such a thing as the Milky Way to start with and stuff fell on the Milky Way. What there was an assemblage of lumps. There's stuff that we now see with the James Webb, actually see it. So this was like 13.5 billion years ago. These little bumps and lumps, all occupying the same broad region of dark matter. And they were each individually forming their stars and lumping together. Now, this process, as we now know from the James Webb, happened much earlier than it was believed would happen, and even just 2 years ago. So it seems to happen very quickly, is that you got what we might call a proto-galaxy or a mini Milky Way, and then stuff rained in on that.
Are there any things, after an amazing career, starting with a PhD where you taught yourself and were unsupervised, that you're disappointed by? Are there any things you think, I really wish I had got the answer to that, or I wish I had another career so I could follow to see where that is going?
The thing that I'm not disappointed about, but I'm intrigued by, is the fact that the elementary particle physics has gone nowhere in finding what dark matter is. And so that is already making it look like the answer is actually probably a bit more interesting than everyone's been assuming. No, there's no point saying I'd start my career differently, because it's going to take decades probably, or possibly much longer, before people work out what's going on there. But that's one to look out for. It's just quite possible that we've actually got this quite wrong, and that whatever cold dark matter, whatever we call cold dark matter is, it's not just another heavy neutrino or funny elementary particle. It's something really fundamentally interesting. And that'll be a fun place to know the answer to.
Thanks very much to our titan of science, Gerry Gilmore. Next week, now we've learned all about dark matter, we'll hear all about the other side of the equation, and that is dark energy. Nobel Prize winner Brian Schmidt will be here with the story of how he discovered that the universe isn't just expanding, the rate at which it's growing is also accelerating. What's that mean for the ultimate fate of the universe, and what's driving it? If you'd like to get in touch in the meantime, the email address is chris@thenakedscientist.com. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the team, thanks for listening and goodbye.